here, A and 7, these are stop autonomous systems. Here are transit autonomous systems. So what is the difference? So there's this distinction between what is local traffic with respect to a specific autonomous system. Yes, local traffic is traffic where the source or destination is within that autonomous system. Transit traffic is traffic where neither the destination nor the source are within the autonomous system. So that's the distinction of whether somebody is a stop network or a transit network. A stop network has, let's see, transit, only transit networks carry transit traffic. U of T does not carry traffic that goes from University of Waterloo to Microsoft. I hope that. Yes, it only carries traffic where traffic is coming from U of T or traffic is going to U of T. So networks that are not transit networks, these are stop. Stop network. There are two different kinds. There is a kind of this red key stop that has a connection to one other autonomous system and does not carry transit traffic. A multi-home stop autonomous system is an autonomous system that has a connection to more than one stop. So if I make a connection here from this autonomous system, or let's say even AS6. AS6 in this example could be a multi-home stop network, but also could be a transit network. So AS6 could be like U of T. U of T is a multi-home stop network. It has connection to Canary or to Orion, where the university traffic is going. It has a separate internet service provider for just public internet traffic into the commercial internet. So U of T is a multi-home stop network. Now, if you're looking at the topology, it's not easy to tell whether a network, an autonomous system, is a multi-home stop network or a transit network. A transit network must have links to two other autonomous systems at the minimum, because if it's not the source and the destination, if it only has a connection to one other autonomous system, what is it doing in the internet? Yeah, it's not. So, but if you're having more than two connections to other autonomous systems, doesn't mean it makes it a transit network. So what makes the difference? And that's crucial to know. The crucial thing to learn about stereo gateway protocols. So interdomain routing, it's policy. That's a routing policy. That's what we're talking about. All right. So here is now what I have here. This is the picture that we're going to use. We have the autonomous systems, and then the connections. These are I indicate the symbols that they indicate routers. These are routers that talk the interdomain routing protocol, and the routers the routers that connect to another autonomous system. They generally talk interdomain routing protocol. So in this example here, AS5 is a single home stop network. So is AS2. AS1 and AS3 and AS4 could be anything. Turns out here AS1 is AS3 and AS4 are transit networks. AS1 is a multi-home stop network. Very difficult to, from looking at the topology here, it's not apparent. There's something more that makes that decision. and that is where routing policy kicks in. So what are the rules in such a setting? So autonomous systems have policies whether they carry traffic or not. Transit networks decide what kind of traffic they carry and to whom. It's called selective transit. Yeah, so in this example, AS3 carries traffic between AS1 and AS4, and it carries traffic between AS2 and AS4, but it does not carry traffic between AS1 and AS2. That would be specified also by a routing policy. Why does it not do it? It's a transit network, there's a connection. Well, because the carrying traffic is engaged in a traffic contract, there's a service agreement that is being paid for, and AS3 to carry traffic from AS1 and AS2 may want to extract revenue. It doesn't get it, so it does not carry. So this here, what AS3 does, selectively carrying traffic between autonomous systems. That's a policy. It's a policy that AS3 and that's so for them to understand policies on the internet, there are two types of relationships between autonomous systems. There is the customer-provider relationship, and there is a peer relationship. Now, the customer-provider, a customer has a provider. A provider may be a customer of some other provider. We have seen this hierarchy of tier 3, tier 2, tier 1. That's exactly what the hierarchy comes from. A tier 2, tier 3 provider is a customer of some other provider, a tier 2 provider. Tier 2 is a customer of some other provider, of a tier 1 provider. Okay, so a stop network obtains access to the internet through a transit network. Well, transit network is a provider, may be a customer of another autonomous system, which acts as the provider. Now, as regard to the customer-provider relationship, the customer is the provider. If you're having somebody as your provider, you're paying for that. So this is, you have to also understand how this U of T's relationship comes about. So U of T has the government paying, or provincial government paying for the research network of Ontario, the federal government paying for the research network of all of Canada, and they think, yeah, this is for research purposes, and then you have thousands and thousands of students in the dorm doing BitTorrent, and then Canada says, we don't have the Canadian taxpayer support these illegal actions that violate the laws that we're setting in Ottawa. That's a routing policy. That asks for a routing policy. It says Canary does not carry traffic that goes to Facebook. See, that's a routing policy. So, and then, because of that policy, U of T is forced to get another provider and then has that customer relation. And then the provider, the commercial provider then says, well, I take everything you paid me for. While the government network says U of T, well, this is all being taken care of you by the government because we want you to get educated and do research. So so we have our business customer-provider relationships are business. The customer pays the provider, and that's how the provider makes revenue. Okay, so this is now if traffic goes between autonomous systems, traffic goes from the customer to the provider, and then the provider is then sending the traffic down. There is no customer. The ASA does not is not concerned with the traffic that goes between AS5 and AS7. AS7 pays for all incoming and outgoing traffic to AS5. That's not that AS is likewise. If traffic goes between AS6 and 8, then the traffic then goes AS8 pays AS5 to carry its traffic. AS5 pays for AS2. AS4 pays AS2, and AS6 pays AS4. That is the business relationship. These are the business relationships. 1, 2, 3, 4 interfaces, 4 contracts in place, 4 places where money is being made, revenue is being extracted, to exchange the traffic. And it's only the relation where money is being exchanged is only at the interface. You are my provider, I pay you. It's not my traffic is going through some autonomous system. Each time I want to send an IP packet through AS4, AS8 has to drop a coin in the that's not how it works. That's important. Otherwise the relationship would be very complicated. Yeah.
So it doesn't matter which way traffic goes from AS4 to
AS4
pays AS2, yes. It would have that relationship. Everything can be a policy. They can specify. There will be a policy about the amount of traffic. They will pay for 100 megabits per second. It could say like your contract at home, where you're having your DSL connection or your cable modem connection, where you have your downstream is much larger than the upstream. You're having a different bandwidth limit in each direction. But if you're paying DSL, if you're paying for your service to your service provider, not based, your subscription includes upstream and downstream. That's your contract. The same with your 3G phone. Your data plan, it's both upstream and downstream. Even though the rates that you get and the limits that you may impose on it, so you're kicking in a different rate plan, may depend on the direction of the traffic. Now, transit networks, in addition to this hierarchical connection here, also have peer relationships. Peer relationships peer relationships are established by transit networks to carry traffic mutually. How does it look like here? AS3 and AS2 if they have a peer relationship, that means if there's traffic between AS5 and AS6, that AS2 says, well, I carry your traffic from AS5 to AS6 based on that peer relationship. I carry any traffic that you send me that has a destination, where the destination is one of my customer networks. So like a business, like an agreement. I take the traffic, and then AS2 says, well, I do the same. That's the peering agreement. Important on the internet, peers generally do not pay each other. Peering relationship, there's no money exchange. It's an agreement. We have customers. Verizon goes to, or Bell Canada goes to Rogers network and says, okay, let's peer. I take your traffic of your customers, and you take traffic from my customers. So that what that accomplishes is that both customers in both customers of either network can exchange traffic. It's a peering relationship. You could pay somebody else to carry that traffic. Yeah. So what's the advantage here? If Rogers and Bell Canada did not have a peering agreement, well, they would either have to be each other's customer or provider. One has to be higher up, Or they both have to have another higher level network where they are both customers to that provider, which then makes this connection, which costs money. So peering reduces the cost of running a network. Yes?
Can be a customer and a provider can service. Like I'm a customer but I'm a provider as well. There's one relationship like that. Like I pay for your traffic and you pay for my traffic.
That seems infinite.
Wow.
But like if it's different traffic, I think.
In that setting, it would still be a peering agreement, essentially. Yeah. When I say
like no one wants to pay.
This is all the real world, normally. Yeah. So in that case, if the network, it would be very asymmetric. Saying that one gets Roger sends networks, sends 10 gigabits per second into Bell Canada. Bell Canada is only 10 kilobits going back. And we're saying, well, that's an uneven peering relationship. But then you would say, well, if that's the case, then what should really happen is that I'm really a customer. You know, the one that asks the other one to carry more traffic should be a customer. The other one becomes de facto a provider. So the peering relationship is driven by mutual benefit. There's a mutual benefit of us making a direct connection because we both avoid having another customer. Now, this is about peering. So peers carry traffic for one another's customers, but they do not provide transit between peers. On the internet, these kind of things do not happen. You do not go from AS6 into going from a provider into a peer again. It's not done. Yes.
Professor, I'm just wondering, when you talk about the cost of traffic, what's the major factor to this traffic, to the cost of traffic? Like, for example, in AS2 and AS3, they are pairs, so they don't pay. From us, we see outside, they don't pay each other the cost, but actually, I think they share the cost of the traffic, right?
They have operational costs, but they don't have a. Yes.
But my question is because they share between, they have the peer relationship because they want to eliminate the cost to provide another AS so that they can reduce the cost. But my question is what does the cost mean while we say the cost of the traffic? What's the major factor that contributes to the cost?
So the cost that is incurred is not. There's the cost that is incurred in running a network. It's kind of business. It's like capital costs, capital expenditures, and OpEx, operational expenditures. That's the cost of running the network. Then, kind of the cost of purchasing a service, that's decided by the market.
Okay.
Yeah, it's a market price. You're going out and want to have this. It's not so different from you wanting to have high-speed access at home. You're looking at who are the providers, what are the options available. You can use DSL, you can use WiMAX, you can use cable modem. So you're making essentially a business decision, and there's the marketplace that determines the rates that you pay for. See that? So it's really like a contract. Sharing costs for running the network, it's more, we're
more benefits than provide others.
Yes. But you see that because of this relationship, this mutual benefit of peering, AS2 should not carry traffic between AS1 and AS3, because then everybody would just throw their network into one other's provider. And you'll see that networks actually between, on any peering relations, nodes, networks already do that. It's called hot potato routing, something that appears naturally in interdomain routing, based on the way that routing policies are implemented. So that's important. Peers do not provide transit between peers. What it also means, yeah, so kind of this is the thing, is at the, so how does traffic go from AS6 to AS4? It's a good question. In this topology, it would not go. So what does it mean? At the top level, all autonomous systems must be connected to each other. All autonomous systems at the top level must be connected to each other. Must have a full mesh at the top. Yeah. So if AS1, AS2, AS3, these are the top level. If there's no other provider above this, then there must be a peering relationship between AS1 and AS3. And this also defines this concept of tier 1, tier 2, tier 3 network. Tier 1 networks, tier 1 autonomous systems are defined as networks that are not a customer of anyone. They only act as providers and as peers. They're not customers of anyone, which means they do not pay anybody for carrying traffic. That's the rule. If you're paying somebody to carry traffic, you're not a tier 1 service provider. Yeah? Paying in the sense of having a customer-provider relationship. Okay. So this is what the business. This is what drives the internet. These are the business relationships. Now, for peering, there are these peering relationships that are set at these internet exchange points, these data centers. There are also private peering. These are called public peering. The private peering is then a peer relationship that does not go through these public internet exchange points. All right. Yes. So the advantages of peering. You can look at this in the traffic between AS7 and AS4. Even at lower layers, can you have peering? And what does peering do? We actually already discussed it. If AS4 and AS5, if there's a lot of traffic between AS7 and AS4, then if AS4 and 5 establish a peering relationship, they both can reduce their cost. And so this example is AS8 and AS4. Before peering, both AS4 and AS5 have to pay their provider network for carrying traffic between AS4 and AS8. If they establish a peering relationship, then they don't. So in this way, peering relationships grow organically. Providers looking at opportunities to reduce their costs. Peering relationships can be helpful to reduce costs, but also they increase the complexity of the network. All right, so that's about routing policies. So now the next topic is how to get these policies realized. And it's all done by a single protocol. And it's done in the most simple fashion. Policies are realized by advertising patterns, selectively advertising patterns. Policies are realized by selectively accepting and rejecting incoming advertisements for path. If I have, the protocol that does it is BGP, Border Gateway Protocol. It is there's only one interdomain routing protocol running on the internet. That is it, BGP. In its version 4, this is the protocol that realizes all the routing policies. It's essentially a distance vector protocol, and it does the path vector, but path vector based on autonomous systems. So it records the entire path. This way, these loops can be avoided. Traffic is exchanged using TCP. Yeah, so a BGP router talks to another BGP router like in a client-server relationship, sets up a TCP connection, and that's where the routing messages are sent through. That's really an application layer protocol. Okay. So BGP, everything is done. With BGP, autonomous systems learn about networks that are reachable, disseminate information about reachable network, and if there are multiple routes to destination, BGP pretty much boils down, kind of provides the selection of the route. Yeah, this is really important. Messages. We're really more concerned with the update message, then different message types. Let's not talk about the message types so much. Let's try to understand the interaction that BGP has. So, routing is based on destination IP addresses, like the ones here. Network addresses 128.100.00/16. Now, autonomous systems in BGP routers advertise prefixes to them. So this BGP router here talks to this BGP router there, and it exchanges prefixes 128.100.00 that are reachable through this network. Now, BGP, we have two routers. Routers that run the BGP protocol, they are called BGP speakers. They speak BGP. That's just it. The TCP session that is established, the TCP connection, is called a BGP session. Yeah, and it has a defined port number 175. That's the port where the BGP service sits on. Then what routers do is they exchange the BGP route, and then they periodically send incremental updates. They never dump the entire routing table because the routing table is long, several 100,000 entries. They only send increments, so it's a stateful protocol. One thing that I should say is in a network, going back to this setting here, in a network like this one here, if you're having some itsy-bitsy tiny autonomous system, it does not need to run BGP. It will just, this is just a small ISP serving a small community. They just may set a default route. That's enough. So if this is here some kind of basement type of internet service provider in a small town, does not need to run BGP, but then has to use essentially a default route. Yeah, so it's not, because BGP configuration is not particularly easy, and bad things are happening if the wrong announcements are being made. Okay, got this. Here, this is the basis of the BGP interaction. We need to now glue together. Everything is based on destination IP addresses, but now we're routing between, sending announcements between autonomous systems. So, autonomous system A, let's suppose it contains network 10.0.0/24. If it wants to allow autonomous system A wants to allow network B to send traffic to 10.0.0/24, anything in here, then it advertises a path to this network. Yeah, so this BGP router here, by sending an advertisement, an announcement of the route to the other BGP router, it essentially says, I'm willing to carry traffic with that destination address. And then router B can then say, okay, I set up a routing table, destination network 10.0/24 goes into whatever then the IP address is of the BGP router in autonomous system A. That's how it goes. Now that's the link. And so that's the okay, so now there's a distinction between BGP sessions that are in different autonomous systems and BGP sessions that are between multiple BGP routers in the same autonomous system. For routing between autonomous systems, each autonomous system should look the same independent of the router where it's being approached from. So what has to happen is that the routers of the same autonomous system, they need to internally exchange all their routes that they learn from each other. If the router over here, if this router on top learns a new path that is being announced by this router from AS Autonomous Systems B, then these routers also need to learn about it. Otherwise, they don't know that this route exists. So that's the kind of the difference being made between internal and external BGP sessions. And the sessions, yeah. So let's see. The rule is essentially this: that whatever update an BGP router of the same autonomous system receives from the outside, it must disseminate that path directly to every other internal BGP peer in the same autonomous system. So this router on top learns about gets an update about a new path or an updated path, it must send an update to all other BGP speakers of the same autonomous system. So essentially, there must be a full mesh between between all in IBGP peers. Now, because this gets very complex in large networks, what large networks do, like Bell Canada already does something like this. Instead of having these mesh of TCP connections between all internal BGP routers, there's a central database. It's called the route reflector, which acts as the central database for all BGP data of that network. Yeah, and then each BGP router of the same autonomous system gets updates from that route reflector. An update comes in from somebody else, it's being updated directly into the route reflector. Something is, who then pushes it out to all other BGP routers. Yeah? So that ensures that all BGP routers of the same autonomous system have a consistent view of how the rest of the internet looks like, what policies are active, which routes are being carried, and which not. Okay, let's now look at what is communicated in an update of a BGP message. So BGP message advertises the path. I said that. So what is being announced in a BGP update is essentially an advertisement for a path. I advertise a path to network 128.100 to you. That means I'm willing to carry all traffic to 128.100. I'm willing to carry all of U of T's traffic. I don't want to carry traffic that goes to U of T. I then withdraw the announcement. Yeah, there is also this message. There's the update. What do I have There's the update. An update is also withdrawal. An update wherein the route is withdrawn. You're subtracting an announcement. Or you frankly never advertise it in the first place. So there's a network prefix being announced. Together with that are a set of attributes. There's a long list of attributes in the order of 20 to 30. What is important to understand, BGP is 3 attributes: the origin, the AS path, and the next hop. So that's what we do. This is the situation here. So what we're dealing with here is that the net AS1 is advertising a path to destination network 10.0.1.0/24. It sends an update message to AS2 and AS3, who then, by themselves, in turn, sending out. The originator of the autonomous system is carried as an attribute. So AS5 can determine if when it receives a BGP update from a router in autonomous system 3, that the originator of this network, this is essentially, can tell where is, in which autonomous system is 10.0.1.0 located. It can say, well, it's origin 1. So you can tell where something is located. This important one for the routing is the AS path attribute. The path attribute essentially records the path that is being taken. So the path follows the reverse direction of the advertising. Let's look at it. AS1 is advertising route network 10.0.10 to AS2. When AS2 advertises this network, it will then say, it advertises to AS4, it says, well, I advertise this path to you, and the path is 2,1. Entire path through the autonomous system. If it gets to AS5, the path attribute is 4,2,1. So that AS5 knows what path the traffic will take. With this, AS5 could now send traffic to a router in AS4, and it would know the set of autonomous systems that are being traversed. If one of the autonomous systems is a competitor or a government enemy, then it could avoid that path by not sending traffic in this direction. Okay? So this is how this goes. Now look at this. AS5 learns about a path to network 10.0.10 from different directions. So now I have to make a decision which one to take. Also policy that is being made. Next attribute, or the last attribute that we need to discuss, is the next hop attribute. The next hop attribute makes then routing possible. If I know the autonomous systems number, I don't know how to set my routing table. For my routing table, I need to have something like destination network 10.0.10, and then I need to have a next hop address. So I need to have the address of a router that I can put in the routing table. Because if you put into your routing table autonomous systems, you can. The routing table is what you have been working with. Yeah, both in Linux as well as in the iOS setting. Yes.
What does the package know what does the package know the autonomous system number? Why can't the path just have the IP address?
Yeah, so you don't. Well, you remember this anomaly that existed in that essentially with this path announcement has the flavor of a distance vector routing protocol. So what this is susceptible to is to have count infinity and convergence problems. if one thing, if you're carrying the path, then the entire path, then you would never run into a loop. Because if you find yourself in your autonomous system, if this path announcement here to AS5, if the path attribute would contain 5, it would not be advertised anymore. Yeah, so you avoid loops in this way. The other one is really plainly this, that you know where your traffic is going. So you know essentially the businesses that we're going to finish with. Let's see, I'm running towards the end. I need to complete this tomorrow morning. So the next hop attribute, because we'll touch on that tomorrow again, because the important part then is how the routing table is constructed from the intra-domain routing protocol plus the next hop attribute of the BGP network. This is complicated.